Okay, so this is question number 31 of the Magnetic Fields homework booklet. So in part 1, we are asked to outline, so really just state what the essential features of a step-down transformer are when it's in operation or when it's working. So there are 3 parts to this. We could kind of say what a transformer is. We could say what the features of a step-down transformer are, and also what the features of a transformer are when it's in operation. So if we start off with the transformer bit, that's kind of the second bit on here, we could say that a transformer is an object that has got coils of wire wound around a core. In terms of a step-down transformer, the primary coil has more turns on it than the secondary coil, and when it's in operation, then the input must be alternating current for it to work, because it doesn't work with DC current, because then there's no constantly changing flux linkage, so there's no constantly induced EMF. So they're the 3 points they're the 3 essential features of a step-down transformer when it's working. Provided you've written down 2 of those things, then you get 2 marks. We then come on to part 2. Now, part 2 basically asks you to do a bit of writing. So what it asks us to do, it asks us to describe 2 causes of energy losses in a transformer, and then discuss how these energy losses can be reduced by either altering or designing the transformer in the correct way, or by choosing the right materials. So altogether there are 4 answers that you can give for that, but we're just asked for 2. So the first one is, so we're going to break it down into why it is that energy losses happen and how you can stop that. So for the first one, we're going to think about what happens when you've got current in a wire. So alternating currents are in a primary and a secondary coil. Because the coils have resistance, then the currents cause heating in the coils, and that part is your energy loss. So that's the first part. And then we're going to say how we can reduce this. So you can reduce losses by using a thick copper wire, because A, if it's copper, it's got low resistivity, and B, if it's thick wire, then it has a lower resistance. And you can then extend your answer by saying that this is most important for the coil that carries the largest current. So for example, if you've got a step, if you have a step down transformer, then the current goes up, and so in the secondary coil you'd have a larger current. So that's kind of getting at that type of idea. So that's one way that energy losses can happen in a transformer. Second way, in this case we're going to think about what happens inside the iron core. So you've got a magnetic flux that passes through the iron core, which is continuously changing, and the core is being cut by this flux, and so this changing flux induces EMFs in the core. If you have a continuous core, so basically you've almost got like a circuit, these EMFs induce eddy currents, and the eddy currents heat the core and cause energy losses. So the first part of that answers the first part of the question about how energy losses happen. You can't just say eddy currents make the core hot. You've actually got to say how the eddy currents actually come about. So that's the first part. And then we look at how we reduce these eddy currents. So they can be reduced by laminating the iron core. So instead of having a continuous core, you have very thin layers of metal that are surrounded by thin layers of an insulator. And if that happens, then currents can't flow in a conductor which is discontinuous or not a continuous conductor. So again, what we've said is how these energy losses happen, and then secondly, how we can stop them. Then we have to go onto a separate page for our third one. So our third one is looking at, again, the core, but in this case, the actual energy required to actually make it into a magnet and then demagnetize it. So that's this hysteresis idea. So what we've got is we've got alternating current in the primary coil continuously magnetizes, demagnetizes, and then remagnetizes the core, and that happens in opposite directions. Energy is needed to both magnetize and demagnetize the core, and this energy is wasted as heat. So that's our wasted energy part, and then how we get rid of it. The amount of energy wasted can be reduced by choosing a material which can be easily magnetized and demagnetized, which is a magnetically soft material. That term is incredibly important. And then give an example, such as iron. So again, we've said how these energy losses can happen in terms of the physics of what's going on, and then how we can reduce these losses. And then finally, the last part So this is our fourth way that transformers can be inefficient. So for transformers to be efficient, as much as the magnetic flux created by the primary coil has to pass through the secondary coil as possible, otherwise you end up with flux leakage. This won't happen, so lots of the flux won't go through the secondary coil if the coils are separated from each other. So these magnetic losses, and that term is really important again, so these magnetic losses can be reduced by having coils that are really close together. In actual fact, a better design would be to have the turns of wire on the same part of the core, but where the core also surrounds all of the cores of wire. So what you could have is you could have a core that's shaped like this. So there's like a central part to it, and then the iron bit also goes around the outside. Your primary coil comes in and goes around the core and goes away again. Your secondary part comes in and then goes around the same part of the core, but you've also got this iron core around here, so that any magnetic field that is channeled away then comes back round again. So again, what we've said when we answered the question is we explain the physics of how you could how you have transformers that are inefficient, and then explain how we could improve the design of this in order to reduce these energy losses. So then we get to part B. So in part B we've got a TV set, and they can be left in standby mode, and that's very convenient because it's available for instant use. However, when equipment that's left in standby mode uses or consumes a small amount of power, the internal circuits operate at a low voltage that's supplied from a transformer, and the transformer is disconnected from the main supply only when this power switch here is turned off. So what you've got is you've got your main supply coming in, you've got your transformer, then this goes to your internal circuits at 9 volts. So you've got a step down transformer from 230 volts down to 9 volts. And we're told when it's in standby mode, the transformer supplies an output current of 300 milliamps at 9 volts. So there is a small current flowing. We need to calculate the amount of power that's wasted in these internal circuits when the TV is left on. So if we're using this current, this potential difference, then to work out the power, we just multiply these two things together. So we've got 300 milliamps multiplied by 9 volts gives us 2.7 watts. For part 2, we're then told that the efficiency of the transfer is 0.9, so 90%. And we're asked to show that the current supplied by the 230 volts main supply under these conditions is 13 milliamps. So we go back to this equation. So efficiency is basically the power out divided by the power in. So if we rearrange this, the power in is equal to the power out divided by the efficiency. Now the power in is equal to the 2.7, because that's our power out, divided by efficiency, which is 0.9, which gives us 3 watts. So if we go back to our diagram, we've got 3 watts of power going in here, and then the potential difference is changed from 230 down to 9 volts, and only 2.7 watts comes out here. So we're wasting 0.3 watts in here. Right, so that's our power in, but that doesn't quite answer the question because we're asked to calculate the current. Now, the current, if we know the power and the potential difference is given by this equation, so power is current times by voltage, and we've rearranged it. So the power going in is 3 watts. The potential difference going in is 230 volts. So if we just work that out on our calculator, you get a current of 1.3 times 10 to the minus 2 amps, which is 13 milliamps. So there are 2 marks for this, one for working out the 3 watts part and one for working out or showing this part, this calculation here to get 13 milliamps. For part 3, we're then told that the TV set is left in standby mode for 80% of the time, and we need to calculate the amount of energy in joules that's wasted in 1 year through standby mode. So and we're also very helpfully told that 1 year is 3.15 times 10 to the 7 seconds. So we want to know how many joules of energy are wasted, and we know the power and the time. So the power is 3 watts. The time is this thing here, because the 3 watts is going in, and although the transformer is not 100% efficient, this 3 watts is constantly being used whenever it's on standby mode. So that's the power it's using whenever it's on standby mode. That's the time. So we've got 80% lot of this year here. So that's our total time, just 0.8 multiplied by the number of seconds in a year. And so energy is just power times time. So it's this 3 watts multiplied by this time here, which is all of this here. And if you do that, you get 7.56 times 10 to the 7 joules. So that's how much energy is wasted. And for doing all of that, you just get 1 mark for the correct answer. Okay, so part 4. So for the last part of this section, we need to show that the cost of wasted energy is going to be about £4 if the electrical energy is charged at 20 pence per kilowatt hour. So again, it's a show that question, so we need to show that it's roughly £4. Now, what we do know is we know how much energy is wasted, because that was this part up here. So we know that 7.56 times 10 to the 7 joules are wasted. Unfortunately, we don't know how much it costs for a joule. So what we need to do is we need to work out, for example, how many kilowatt hours we've got. Well, 1 kilowatt hour, to convert into joules, a kilowatt is 1,000 watts. So if we multiply 1 kilowatt hour by 1,000, that'll give us an answer in watt hours. And then because we've got 60 lots of 60 seconds, again, if we multiply by that, that tells us how many joules there are in 1 kilowatt. So 1 kilowatt hour in joules is 3.6 times 10 to the 6 joules. So what we can do is, first of all, we can work out the number of kilowatt hours that are being wasted. So this was the number of joules that we had that were being wasted, that we worked out in the previous part of the question. This is the number of joules that are in 1 kilowatt hour. So if I do this number divided by this number, it tells us how many kilowatt hours of energy we've got. And if I do that, I get 21 kilowatt hours. Now we're told in the question that electrical energy is charged at 20 pence per kilowatt hour. In other words, every kilowatt hour worth of energy costs 20p. We've used 21 kilowatt hours altogether in this year, so the cost will be 21 kilowatt hours times 20 pence. So basically it gives us 420 pence, which is £4.20, which is approximately the £4 that we're looking for. In terms of the 2 marks, basically getting the 21 kilowatt hours is 1 mark, and then showing that the cost is £4.20 is your 2nd mark. Finally, the last part of this question, part C. We're told that the power consumption of an inactive desktop computer is typically double that of the TV when that's in standby mode. And the waste of energy, this wasting energy, can be avoided if you switch off the computer every time it's not in use. We're asked to discuss one advantage and one disadvantage of doing this. So basically, we just have to say what an advantage is, really, and what a disadvantage is. So an advantage, turning it off saves money because less energy is wasted. So we've said the advantage and why it's a good thing. Disadvantage, although it does save you money, a disadvantage is that you have to wait for your computer to boot up. And why is that a bad thing? Basically because it's inconvenient. If you write that advantage down and you write that disadvantage down, you've got 2 marks. So that was question number 31 of the Magnetic Fields homework booklet.